Okay, hello everyone. Welcome back to the online causal inference seminar. This week we have Vasilis Syrgkanis, who recently joined Stanford University, and he will talk about automatic debiased machine learning for dynamic treatment effects and general nested functionals. Our discussant will be Tchetgen Tchetgen from University of Pennsylvania. Today's Q&A will be handled by Emma. And I'll hand it over to her to explain the rules.
Hi, everyone. Thanks for coming. So yes, as Chungyeon said, I'm handling the questions today. So please submit your questions through the Q&A, not through the chat. And periodically, I think Vasilis will stop and ask for questions, and then I will read them out to him. So feel free to submit your questions as soon as they come up. You don't need to wait for a particular time. They will be stored here, and we'll just wait to ask them. All right, that's it. So Vasilis, you can take it away.
Great. Thank you very much for inviting me. It's a great seminar, and I'm very happy to present. So today I wanted to talk about a recent line of work that we've been working on automatic debiased machine learning with generic machine learning for static and dynamic causal parameters, building up to the paper that's associated with the talk, which is on automatic debiased machine learning for dynamic treatment effects. I'll spend quite some time building up to that framework and giving an overview of these first few papers so that people can understand the more general framework that's presented in the most recent paper. First, let me start by trying to motivate why we need automatic debiased machine learning. And I just want to first mention that we are currently at a stage where everybody with an access to a data set and an outcome of interest can construct an ML predictive model. So using AutoML frameworks that are out there. So using predictive machine learning is super easy for domain experts and not machine learning or statistics experts. And we should strive to make causal machine learning as easily accessible as automated machine learning to every decision maker, so that domain experts with access to a data set and an outcome of interest can address interventional questions that they have in mind. The problem with that is that predictive modeling is vastly harder than causal modeling. In predictive modeling, you just have three stages. You collect your data, you estimate, and then maybe you validate on a separate data set, or you split your sample and validate on the other half. And maybe nowadays you also try to interpret what is learned. But in causal modeling, you need many more steps that require a lot of human-computer interaction. For instance, you need to elicit domain assumptions. You need to devise an identification strategy based on the domain assumptions. And there's no such perfect analog as out-of-sample validation for causal modeling. And so for that, it's important that we do sensitivity analysis to check how our results change based on domain assumptions. And also because there's no perfect analog of out-of-sample validation, we care a lot about constructing confidence intervals and performing inference. In fact, exactly because there's no perfect analog of out-of-sample validation, the causal inference pipeline is really a loop where we want to use already collected data to inform what experiments we want to run next and test our hypothesis. There's been a lot of tools that try to address many of these components of the causal inference pipeline out there. There's yet to exist a single tool that a domain expert can use and interact with and answer a causal question or define the most informative experiment. And the problem with that, I think, is that there still exists a lot of open research questions that need to be addressed in all of these different blocks. A lot of the emphasis has been on the estimation and inference in the last few years of the causal machine learning field. And a lot of my work lies in that, but we need to put a lot of work also on the other components. In this talk, I'll actually talk about one line of work within the estimation and inference pipeline that goes into this automation sort of like ultimate goal of how do you go from an identified estimate to an debiased estimate so that you can perform inference automatically. And so the reason why we want to do this automatic debiasing is so that we don't need to do math every time that we define an estimate based on an identification strategy and find what is the, like a debiased or a robust version of that estimate and construct p-values based on that. We want to be able to do that automatically. So this is this leads to this topic of automating the debiasing process, and I'll be talking about how can you do that. How can you build debiased estimates of generic machine learning regression estimators with generic machine learning. And then in the first part of the talk, I'll mostly focus on static treatment effect cases. And then we'll see how that approach that we built generalizes to dynamic treatment regimes and general nested functions. To make matters more concrete, I'll be focusing in the beginning on a particular class of causal estimates, which are estimates that are based on linear moment functionals. We will assume that the parameter of interest theta is defined based on a linear moment function. It's the expectation of some moment m, which is linear in some function g, and that function g is defined as a regression function. So g is the regression of y on x. Classical examples of this setup include the average treatment effect, where under conditional unconfoundedness, where if you assume that conditional on x, the potential outcomes of y are independent of the treatment, then the average treatment effect can be written as the average of this large regression function that regresses y on t and x, evaluated at t equals 1 and at t equals 0. Similarly, if you don't care about the average effect, but you care about some average policy effect, where the policy pi maps observed covariates to treatment or no treatment, that also can be phrased as the average of a linear moment functional. And if you have a continuous treatment and you care about the average marginal effect or the average derivative, that also corresponds to a linear moment function. Our goal is to be able to construct confidence intervals for theta while allowing for machine learning estimators to be used for g, or in cases where x is high dimensional, either in cases where x is high dimensional or in cases where x is low dimensional, but we want to be non-parametric and flexible, and we want to use techniques like random forests. To do that, we need to remove the bias from the estimation of g. Typical machine learning estimators will try to balance bias and variance, and that bias in the estimation of g is going to propagate into the estimation of theta, and the estimate of theta is not going to be centered and might also incur a large error because of the error of g. The solution to that is to debias the moment by adding a correction term. The correction term roughly tries to say whenever your g is biased, meaning that it does not predict, it does not equal to the expected y conditional on x, then that residual over there is not going to be mean zero. And so whenever that is not mean zero, we should try to correct our moment m by multiplying that residual with some function a. And so here this should have been a plus, not a minus. So this is a general form of a debiased moment. And the intuition is, as I said, whenever g is biased, we're going to get some non-zero term, which is going to correct m. The main question is, what is this a that we need to multiply that residual so that we correctly debias the target moment function m? And the answer to that question is that A of x should be what is known as the Riesz representer of the linear functional. So if we view this expected m as a linear functional of g, then by the Riesz representer theorem, and assuming some continuity regularity assumptions, any such linear functional will have an inner product representation in the L2 space, which means that we can write this linear functional as an inner product of the form expected value of A times G. And that A is the Riesz representer. So in order to debias the moment M, we need to be able to estimate that Riesz representer and add this debiasing correction. Why is that debiasing correction useful? The general theorem is, suppose that you estimate your moment based on an empirical analog of that debiased moment, where you plug in some estimate of G hat and some estimate of the Riesz representer A hat. Then if the moment satisfies a regularity condition known as mean squared continuity, it's a slightly stronger version than continuity, because you need the square, the second moment of M to be Lipschitz with respect to the L2 norm of G. And moreover, suppose that G hat and A hat are estimated accurately enough on a separate sample or with cross-fitting, and at the rate where only the product of these two errors needs to go down as 1/√10. So this is sort of like a form of double robustness, where either A minus A hat, for instance, is fast enough, or G hat minus G naught is fast enough, or their product should be 1/10. This, for instance, will be satisfied if both of them decay as 1/n to the 1/4. Then you can show that this empirical estimate is going to be asymptotically normal, and hence you can construct confidence intervals based on that asymptotically normal characterization. So this debiased moment offers this form of double robustness, and the one missing piece is, how do you estimate this Riesz representer A hat? The traditional approach to debiasing is to characterize how the Riesz representer looks like for your target moment of interest, and then perform plugin estimation. For instance, in the case of the average treatment effect, the Riesz representer looks like this inverse propensity term. There are two terms, one for the G1 and one for the G0. So that's the classical inverse propensity term. And where the denominator is the probability of treatment conditional on X. And so plugging it back to the debiasing formula, you'll get the augmented inverse propensity estimator or the doubly robust estimator. Similarly, you can derive the functional form of the Riesz representer for the other moment functionals, and it will typically depend on some other function, like the propensity or the conditional density of the treatment. And then you can estimate that function. For instance, you could train a probabilistic classifier for the propensity and plug it in. However, the automatic debiased machine learning sort of like line of work asks, can we circumvent this characterization step and estimate A directly? We don't want to have to do sort of math every time that and analytic derivations every time that we come up with a new estimate, and derive what the Riesz representer looks like, and then estimate whatever function comes up. Can we directly estimate A solely with black box access to the moment of interest? So if someone just gives you Oracle evaluation, Oracle access to the moment of interest, can you estimate A without knowing how A looks like exactly? And the seminal paper of Chernozyukov, New and Singh showed how you can do this using L1 penalized linear representations of the Riesz representer. And in fact, this idea of estimating the Riesz representer directly dates back to even the seminal paper of Newey 94, which characterized the variance of semi-parametric estimators, or follow-up work by Chen and Liao, and more classical work, which tries to estimate this Riesz representer based on unpenalized linear representations. And typically uses this implicit estimation of Riesz representers not for debiasing, but rather for calculating the correct variance. So here, the works above repurposed, sort of like this idea of automatically estimating the Riesz representer for debiasing. But here, what we're going to ask is, what if we want to do generic ML for estimating A? We don't want to be restricted to using unpenalized linear representations or unpenalized linear representations. We want to be able to use any machine learning method for estimating that Riesz representer without the need to characterize it. And so this was the key idea in this paper on automatic debiased machine learning via neural nets for generalized linear regression, where the key observation was that you can view the Riesz representer as the minimizer of a stochastic loss of a risk. That loss looks like the expected A of x squared minus 2 times the moment evaluated at A. By the Riesz representer theorem, we know that the second quantity over here, the expected moment evaluated at A, is going to be equal to the true Riesz representer A naught multiplied by A. And so you can easily then sort of complete the squares. You can add the constant term, which is A naught of x squared. And once you add that, then you can complete the square and you can see that the loss is equivalent to the mean squared error with respect to A naught that you care about. So minimizing this loss is equivalent to minimizing the mean squared error that you care about. And the other nice thing is that this loss only requires oracle access to the moment of interest. You don't need to know how MZ of A looks like. You just need to be able to evaluate it. And so you can take this sort of like population risk into an empirical estimate by minimizing the corresponding empirical loss, where you replace the expectation with an empirical average of this quantity. And we can show, we can prove estimation rates that scale with a notion of complexity of the function class A that you're using to minimize over. And in particular, we're using the critical radius, which is a notion that typically yields tight measures. It's a tight sort of like convergence rates for strongly convex losses. And here we have a strongly convex loss. More formally, you can show that if you choose a delta n, which upper bounds the critical radius of these two function classes, the first is A minus A naught, and the second is M of A minus M of A naught. And these are just like scalars, scalings of them. So that's also required that everything between that and 0 is included. And your moment function satisfies the same mean squared continuity that I mentioned for the normality theorem. Then you can show that the minimizer of the empirical loss is going to be achieving fast rates, meaning of the order of the square of the critical radius plus some bias error if your true Riesz representer is not in the class over which you're minimizing. And so here I'm saying fast rates because, for instance, for parametric function classes, delta n is typically of the order of 1 over root n. And so you're going to get here rates for the mean squared error that are of the order of 1 over n. And similarly for VC dimension, VC subgraph classes, you're going to get of the order of root log n over n. Sorry, delta n is root log n over n, so you're going to get a log n over n rate. So these are sort of fast rates. You're getting 1 over n rates. So that's one theorem we had in that paper for estimation rates for the Riesz representer. And because it's an empirical risk minimization approach of some loss function, you can see that you can use any ML method to minimize that risk. So you're not constrained to just use L1 penalized sieves or neural nets or random forest. You can use any of those approaches to minimize that loss. And these are just some examples of what rates you're going to get for different function classes that you might want to use. And this approach does not only hold for linear moments, you can go beyond linear moments. If the moment that function that you have is of some of the form expected m of theta naught g naught is equal to 0, where this moment m can be nonlinear in G naught, then you can still locally debias the moment. You won't get double robustness, but you can get local robustness, which is still good enough to give asymptotic normality, and so construction of confidence intervals, assuming A and G are estimated accurately enough. But here the estimation approach is slightly more complicated. You need to estimate the Riesz representer not of them nonlinear functional that you have over there, but instead you first need to linearize that nonlinear functional around some G, some estimate of G. In fact, your goal is to estimate the Riesz representer of the directional derivative evaluated at G naught of that nonlinear functional. And so that's this quantity down here, which is now linear in G. So this directional derivative is linear in that sort of deviation parameter G. And then you want to estimate the Riesz representer of this linear functional, which you can do in two steps. First, estimating a preliminary model of G, applying it instead of G naught, and then doing some sort of like automatic differentiation to estimate the directional derivative, and then plugging that automatically differentiated moment into our automatic Riesz representer approach. So that's the first sort of small part of the talk, and I'd like to stop here and pause for questions.
Thanks, Vasilis. We have 2 questions at the moment, so I'll work backwards. So this question is a bit long. There is a parallel line of work on debiasing by influence functions where we can empirically compute the influence function. How do you compare AutoDML to this line of work?
One thing I should say, it's not clear what, when you're automatically computing influence functions, it's not clear what direction to use in the directional derivative when you're trying to add some extra sort of like perturbation to your probability law. And so it's not clear how you're going to get, you know, what types of guarantees you can get for such approaches, and also not clear if you can get some sort of like mean squared error guarantees for the influence function you're calculating, similar to how we get mean squared error guarantees for the Riesz representer. On the other hand, the two are very well connected. You know, like the influence function for those average linear moments looks like this debiasing thing. So you estimating the Riesz representer automatically is implicitly estimating the influence function, and many times the efficient influence function for its linear moments. And so from that perspective, you can view this as another way of automatically estimating an influence function with some mean squared error guarantees on the approximation error you're going to get.
Thank you. Thanks for answering the question. There's another question. Is it possible to say anything about uniqueness of the Riesz representer?
So there is, yeah, that's a good question. The Riesz representer might, especially if you restrict your function to class G, might actually not be unique. But typically there will be a minimal Riesz representer in terms of, like, say, a second moment. And so that's the one that you really want to estimate. And I believe our loss function will go after that because it has this expected a squared. That's it, yeah.
Great. So we just got another one. So maybe we can have a short answer to this question. Do you have any thoughts on how your framework can incorporate constraints on the parameter space? Is it simply solving a constraint optimization problem to minimize the loss?
Because we're doing a plugin in the end of the Riesz representer, it's not clear how you would do that, right? So in the end, we're still doing the thing that I mentioned so far, we're still doing a plugin to the moment and then estimating an average moment. If you want to estimate an average moment subject to some constraints on theta, it's a harder problem. What if theta lies at the boundaries and then it's not clear how you would do asymptotics? Another thing I would want to say is that you can use our framework also within the TMLE framework. And there maybe you could incorporate constraints on say the outcome being binary or something like that. Because really the Riesz representer we're estimating is equivalent to this least favorable direction that you need to add to the TMLE framework. And so you can use our Riesz representer in the TMLE framework to construct a corrected regression function G. Right, so and then do a plugin with that corrected regression function G. And you can also use our framework also as not in the TMLE, but in the earlier approach of Sarstein, Robbins, and Rudnitsky, where you add the Riesz representer as a clever covariate. So you can also add A of X. You can first estimate A of X and add it as a clever covariate in the regression, regressing Y on G of X plus a linear function of the Riesz representer. And that will also give you double robustness. And maybe those approaches are more amenable to adding constraints.
Great. Thanks for a very detailed and considerate answer. So yes, we don't have any more questions at the moment. So
cool.
Feel free to continue.
Cool. So the next short snippet of the talk is about making this approach practical using neural nets and random forests. And we wanted to take it to practice and see what maybe we can do some practical heuristics to improve the the vanilla method for these particular types of machine learning approaches. And the first observation for neural networks was that you can have a generalization of the Rosenbaum and Rubin result where it suffices to condition on propensity when estimating the regression to get an unbiased estimate of the average treatment effect. This observation generalizes to any linear moment functional. It always suffices to estimate a regression function that is just a function of the Riesz representer. So you don't need really to condition on all of X, but you only need to condition on the Riesz representer A naught of X if you want an unbiased estimate of the average treatment effect. In fact, it suffices to just run a linear regression with respect to the Riesz representer, and you will still get an unbiased estimate of the treatment effect. Although it won't be efficient, but it'll still be unbiased. Right? So the Riesz representer really carries the sufficient information that you need to control for to get an unbiased estimate of your target parameter. And you can view that it's just one line of derivation that uses the Riesz representer characterization. I won't go through that, but we can use that within a multitasking neural network architecture, where we say because the Riesz representer carries all of the information that we need to condition on, we can share a lot of layers. We can have like a first few layers of a neural net leading to a representation that is used in some linear form to learn the Riesz representer. And that same representation that's used for the Riesz representer is then also passed to another smaller neural network that learns the regression function. And so this multitasking hopefully will help learn better representations and deal with the, the fact that the neural networks, those representations are not really identified, but you will have more information when we train both on the Riesz representer and the regression function to learn better representations. And in fact, because you're training both G and A directly, you can incorporate this clever covariate adjustment idea within the neural net training by always adding some linear function of the Riesz representer in your final regression function and minimizing that square loss with the clever covariate. So we can simultaneously minimize all of these losses, the loss of the vanilla G of X regression square loss, the loss of the clever covariate regression loss, and the loss of the Riesz representer all simultaneously, and hopefully that leads to better estimation rates for all of them in finite samples. And that's exactly what we got. This approach actually was inspired by prior work by David Bly's group, which used essentially the analog of our multitasking architecture, but with a plugin formula. So they were using multitasking to learn the propensity and the regression, and then doing the doubly robust at the end with a plugin formula for the Riesz representer. Here we can generalize that to any linear moment functional, and instead of first learning a propensity and plugging it in, we actually directly minimize the Riesz loss, which is the square loss with respect to what you care about, which is the inverse propensity. And so by doing that, we actually get better rates than the DragonNet for the standard semi-synthetic data set that's out there on infant health and development program. So we get like 0.11 mean absolute error as compared to 0.146. And you see here, this improvements primarily comes from the fact that we're not learning a propensity, we're learning the Riesz representer directly. Similarly, we devised a way of training random forests based on the Riesz loss. And there we used the ideas from the generalized random forest work. And we can cast minimizing this Riesz loss as solving a conditional moment restriction. And so we can use these ideas that go into the generalized random forest to have a random forest that minimizes the Riesz loss. And by doing that, we also get very good performance in terms of the mean absolute error. And also we get pretty good coverage in terms of confidence intervals. So we get both small mean absolute error and good coverage. And the nice thing with this generalization to any moment restriction is that you can also take it to continuous treatments and estimating average marginal effects, which was not possible with the plugin approach, the approaches that were before, that solely focused on the binary treatment case. Here, for instance, we applied it to a public data set on gasoline demand, and we get reasonable results. Hard to test whether these are accurate results, but at least we get results for our non-parametric Riesz representer-based estimator of elasticities that are comparable to what you would get if you made a parametric assumption and you estimated an average marginal effect based on a linear parametric assumption. So at least the method does not collapse or give nonsensical results in finite samples. Even for this hard problem of estimating an average marginal effect, where if you were to take the characterization approach, you would need to estimate a conditional density, which is a hard statistical task. But here we sort of avoid this direct estimation of conditional density by minimizing the Riesz loss. I also like to pause here for a few questions if there are for this small snippet.
So we actually don't have any open questions now on the Q&A,
right.
And I think in the interest of time, maybe it's, yeah.
Sure.
Yes.
So let me move on to the more general framework of estimating dynamic causal effects and automatic debiasing for dynamic causal effects. The types of estimate that we now care about are of the following form. We have data that are collected based on a dynamic treatment regime. So treatments were offered in an adaptive manner where, say, at multiple periods, some treatment was offered at period 1 that depends on some observed state. That treatment affected the observed state, and then the observed state at period 2 and T1 led to what treatment was going to be given at period 2. And then in the end, we have some final outcome of interest. And what we care about is understanding what would happen if instead of offering this, if we intervened in the system and offered some sequence of treatments, tau1 and tau2. For now, I'm going to focus just on a static treatment sequence. So we're not looking at some counterfactual adaptive policy that we want to evaluate, but our framework will extend to that too. So we just care about the simple thing. What would happen? What would be the mean average outcome under such a static treatment sequence, tau1 and tau2, say always treating? The setting here is inherently more difficult than one-shot treatment problems because of this this control treatment feedback loop that treatment at period 1 changes the controls or the covariates that go into the treatment decision at period 2. And so this really precludes us from viewing this problem as a one-shot treatment problem. We cannot just say this person was offered 2 treatments, T1 and T2, and let's control for S1 and S2, or let's just control for S1. None of these static treatment reductions would work in this problem and wouldn't estimate the thing that we care about. And so that's why this setting has its own name and is known as the dynamic treatment regime and has a long history especially in biostatistics. But one observation is that even though we cannot view it as a one-shot controlling for exercise, where we just try to estimate the effect of some treatment on some outcome controlling for a set of variables, we can actually view it as a recursive controlling for exercise. We can go in the end, for instance, and say, what if we want to leave the first period treatment as is and just intervene on the second period treatment? What would be the mean counterfactual, the mean outcome under such an intervention? Of course, this is this is just a static treatment problem. We can estimate that by estimating the effect of treatment 2 on the outcome controlling for S2. So based on the G formula, we will just regress the outcome on T2 and S2. And then by the fact that conditional on S2, this potential outcome here is independent of the original treatment T2, which is known as sequential conditional exogeneity. We'll get that when we evaluate that regression function F2 at different treatments, say tau2, we're going to get exactly the mean potential outcome that we care about, right? So F2 of tau2 is the expected Y, conditional on T2 equals tau2, but then that is really this potential outcome over here. And because of sequential exogeneity, we can drop the conditioning on the second period treatment, and we get exactly the mean of the potential outcome that we care about, conditional on just the state. So now, once we do that, if we redefine our outcome to be this adjusted outcome, where we simply impute as an outcome the evaluation of that function f at tau2 at the intervention that we care about in the second period, then it's as if we remove that second period treatment from the equation. So there is no second period treatment, there's no second period state, and we just have another controlling for exercise where our goal is to estimate the effect of treatment at period 1 on this adjusted outcome controlling for S1. Right? So we can estimate a new regression where we regress that adjusted outcome on T1 and S1, and by a similar derivation, you'll get that whenever you evaluate that regression function at any tau1, you'll get exactly the mean potential outcome that you care about, conditional on the first period state. Right? And so in the end, you can look at this, like this new, yet another adjusted outcome. You evaluate this first regression f of tau1. You know that this f1 of tau1 is going to be in expectation equal to the potential outcome that you care about. And so then the average effect that you care about is just an average of that regression function or an average of that adjusted outcome, and you're going to get your target estimate. So this recursive controlling for exercise yields this target estimate, which is based on recursive regressions. So the theta that you care about is the expected value of that regression function f1 evaluated at tau1. But that regression function f1 is a regression that depends on some other regression function f2 evaluated at tau2. So f2 of tau2 is really the label that you want to predict, conditional on t1 and s1. And that other regression function is now really a regression function, predicts the outcome conditional on t2 and s2. So this is the estimate that you want to debias. And you see that it does not fall into the static sort of treatment problems that we were facing in the first part of the talk, because now the function that goes into our linear moment functional, which is the first equation, is not really a regression function that predicts some target variable. It's a regression function that predicts some other regression function, which then predicts some target variable. And this is the idea of the nested regressions, and why like our paper is called estimating general nested functionals. So how do we debias this theta? Instead of just plugging in the direct f1 and f2, say we use again random forests or lassos to estimate those regression functions. We don't want to do a plug-in approach. So how can we use a similar automatic debiasing approaches to debias this vanilla estimate? We can start by following a similar pattern as we did in the first talk, in the first part of the talk. We can add a debiasing correction to our original moment, where the debiasing depends on the residual of the first regression function f1. So that regression function f1 is trying to predict f2 evaluated at tau2. And so whenever that f1 is not equal to the expected value of f2, given t1 and s1, this residual is not going to be mean zero, and you're going to have a debiasing correction that's going to correct the errors in f1. And of course, the thing that you need to multiply over here is the Riesz representative of your original moment function. So that's fine. So this is one step where you can, it's very similar to the static treatment problem. But now you all of a sudden have a dependence on f2, which is another regression function that has not been debiased, right? So the errors in f2 now are also going to directly impact theta, and you're not going to get an asymptotic normality, unless f2 is very benign. So what can you do? Well, this is yet another linear moment functional of f2. So you can view a1 times f2 as a linear moment functional f2, estimate the Riesz representative of that new linear moment functional, and add yet another correction that debiases with respect to f2. So you're going to add one more term over here, where a2 is the Riesz representative of a1 times f2 evaluated at tau2, and it multiplies the whatever like the residual of f2 with respect to whatever f2 is trying to predict. So in this case, it's going to be y, and now we didn't introduce any new sort of function into our moment, so we're done. So this it's a recursive Riesz correction, where at every step you're estimating a Riesz representative of some linear functional, and you're adding the residual of that corresponding regression function with what it's trying to predict. So that's the debiasing idea, and you can generalize that whenever you have arbitrarily stages and arbitrarily sequence of treatments. You continue adding correction terms that look like the Riesz representative of the corresponding linear functional and the residual of whatever the regression function is trying to predict. And under regularity assumptions and under assumptions on the products of rates of the Riesz representer and the regression functions, you can also get asymptotic normality. And here we get, again, this condition on the rates of convergence that is known as, is related to the notion of multiple robustness. You don't get exactly double robustness, but you get that you only need either the Riesz representer at AT and the regression function at time t, or to go down to 0 fast enough at 1 over root n rates. And you also need the Riesz representer at time t and the regression function at time t plus 1 to go down as 1 over root n rates. So you have an extra term over here.
Sorry, Vasilis, if you could
sure.
wrap up your talk in 2 minutes, that would be great.
Sure. All right. Yeah. Great. So that's the main asymptotic normality theorem here. Now, how do you estimate the Riesz representer? We can estimate the Riesz representer using the idea of the Riesz loss minimization, but now it's going to be a recursive Riesz loss minimization. The loss function is going to be AT minus 2 times the moment. The moment at every step is going to be either the original moment or the previous Riesz representer multiplied by the new Riesz representer. So this is going to be the form of the loss function that you're minimizing at every step. And you do that again recursively from period 0 up till the final period. Compared to the static setting, now we need to account for errors propagating from errors in previous iterates of AT, and we provide them a theorem that does exactly that and gives finite sample RMSE guarantees for A hat, for all of these A hats that you're estimating. We also have several extensions of this basic framework, so that grow in complexity. For instance, you don't need to have just this static dynamic treatment regime problem, but whenever you have any set of nested linear moment functionals where the first moment depends on F1 and F1 depends on F2 and F2 depends on F3, whenever you have such nested moment sequences, you can apply our recursive automatic debiasing idea. And this, for instance, captures evaluation of dynamic adaptive target policies. You can also extend that to non-linear recursive moments, and we have an application of that for estimating models of dynamic discrete choice. And you can even go to non-linear nested IV functional, where the conditioning is not the same set of variables as what goes into your function. So this corresponds to non-parametric IV problems at every stage. And we have an automatic debiasing approach for that setting. And you can even generalize that where the expectations of every one of those moments are taken with respect to different distributions. For instance, you might want to use that when doing data fusion, where some regression functions are trained on one data set and then applied to another data set. You can still do automatic debiased machine learning. And this, for instance, has applications to the surrogate approach, where you want to use historical data as short-term data to estimate the effects of treatments on long-term outcomes. And that's all I wanted to say. To recap, a large variety of causal estimates that arise in complex static and longitudinal data analysis can be automatically debiased when regularized machine learning algorithms are used to estimate the nuisance models, and the estimation of the debiasing term itself can be performed with generic machine learning. And experimental results using neural nets and random forests provide examples of superior performance to plugin approaches and to prior automatically debiasing approaches based solely on linear models. Thank you very much.
Thanks, Vasilis. So maybe in the interest of time, we skip the questions in the Q&A now and move on to Eric's discussion. Just know if your question doesn't get answered during the talk, we still pass on all the questions to the speaker, and you can continue those discussions after the talk. All right, Eric, please feel free to share your screen.
Can you see my screen?
Looks great.
Yes. Okay. Thank you. So this is a discussion of Vasilis' work with colleagues. Let me jump right into it. First off, I mean, congratulations. I really enjoyed this paper, as well as the other papers in a series of works by the author and his collaborators. It's a very ambitious program that they have going there. The ambition here is to provide automatic inference tools for some of the most important semi-parametric functionals in the social and health sciences. So the average treatment effect, the average treatment effect when treated, the average derivatives, and many more that Vasilis described, including settings where you have longitudinal data and sequential treatments. And the goal is to come up with estimators automatically that have so-called what has been known in literature as small bias properties. So what is a small bias properties? Small bias properties have long been part of the semi-parametric folklore. It's well known in certain circles. If you're aficionados of that is adept at the mystical art of influence function calculus, that was developed back in the 80s and 90s by famous people such as Bickel and colleagues, Van der Vaart, Newey, and Jamie Robbins. What does automatic debiased ML try to do? It's really, I view it as a democratization of the small bias property into a simple calculus that anyone can in principle follow, unencumbered by notions of tangent spaces, pathwise differentiation, and all these technicalities out of the semi-parametric theory. Despite that, I want to just spend a few minutes talking about, this was also raised as a question to the speaker, connections to modern semi-parametric theory. What is the connection between ADML and this literature? The small bias property refers to an estimator of a semi-parametric functional having second or smaller order bias, a property known to hold for so-called influence functions. What is an influence function? And as you can see, this gets increasingly technical. So roughly speaking, without going into the details, an influence function is you take the derivative of your functional with respect to a path, a collection of pathways in your model, and you look for a representation such that the derivative can be represented as a score under that semi-parametric model, multiplied by a choice, this object V of O. Okay, and V of O is known as an influence function, and so it would be an object that satisfies this equation. If M, the model, the semi-parametric model, is unrestricted, then V and O is unique and characterizes the efficiency bound for the model. If M is restricted, V of O is not unique, and the efficient influence function can be obtained by projecting any V of O onto the tangent space for M. And so this can be a really difficult and tedious exercise, how to solve this equation and find V of O that satisfies this equation for all scores in your model. But there is a connection to what the speaker is doing here. Note that thinking of this derivative, the one I had on the left-hand side, as a bounded linear operator on the tangent space, and so the tangent space is the span of the scores, and so this is a linear operator on the span of the score. Then the equation can be rewritten as you have the derivative. Now I think of it as a linear bounded linear function on the tangent space, and by the Riesz representation theorem, that could be written as one element of that space times a score in terms of the inner product between those two objects, which of course is the right side representation that I had on the previous slide. And so this is an implementation of Riesz representation theorem from the perspective of the functional, not a moment equation, from the perspective of the functional and the semi-parametric model, because that is what defines the tangent space. Okay, and so the efficient influence function VF is the Riesz representative of the functional derivative operator psi of S. And a key property of VF, the efficient influence function, in fact, of any influence function, is that it is a good moment equation. And this has been advocated by many people over the years, that it generates semi-parametric estimators in the model M with second order bias, aka the small bias property we're after. In many examples, the second order bias is of mixed bias type, aka double, multiply robust. You could tell that there are a lot of lingos here, but they all sort of correspond roughly to the same idea. And I would recommend looking at papers by Robbins, Rudnitsky, and colleagues, and as well as Van der Vaart for rich literature on these these types of techniques. Recently, Chernozhukov and his colleagues have rebranded small bias essentially as what's been known as MIM and orthogonality. So if you see a recurrent theme here, these ideas evolve over time and new twists to these existing ideas are added. And so the question is, what is new in ADML? What are as far, in my view, there are two key insights of ADML, which I think are terrific. Typically, the efficient influence function can be hard to derive. ADML gave a very simple approach for a large class of functionals to do this automatically without learning difficult semi-parametric theory. Okay, so that's great. As Vasilis described in many examples, often the efficient influence function, and in fact influence function in general, in order to guarantee this property of small bias, will depend on high-dimensional nuisance parameters nonlinearly. For instance, for the familiar AIPW, it will depend on 1 over the propensity score. And so ADML gives a simple but yet very general approach, generic approach, to estimate these nuisance parameters, i.e. these nuisance parameters become identified by the Riesz representative, that is completely agnostic to the actual functional dependence on the nuisance parameters. These are both cool key insights and very important steps forward, particularly when combined with powerful ideas such as cross-fitting, which, by the way, is yet again, an idea that has been in the literature for quite a while, going back to Schick in '86, which permits the use of now in our modern days, allows us and licenses us to use highly adaptive ML tools and modern learning theory to study asymptotics. So I just thought I would spend 1 minute on a canonical example, which is a one-arm causal inference problem or a missing data at random problem. And so we're interested in the expected value of Y for the whole population. We observe Y only for those who have R equals 1, and condition on L, fully observed covariates, Y is independent of R. And therefore, we have missingness at random. And the observed data functional is, of course, given by the G formula. Take the expected value of the conditional expectation of Y given L among the complete cases. And this is a functional that is pathwise differentiable as long as positivity holds. You have at least this condition event makes sense. The EIF, the efficient influence function of Robinson, Minsky, and Zhao, derived back in '94, is the augmented IPW estimate moment, W robust moment equation, which is given here, combines propensity score and outcome regression in such a way that the bias used by of an estimator that would plug in estimators of these two quantities would in fact be W robust, meaning mixed bias type, the product of the biases of the nuisance parameter. Okay. And so this will typically, for implementation, it will require estimating these two nuisance parameters separately. This has traditionally been done as treating them as regression problems, and whether one uses parametric, semi-parametric, or more flexible methods. And there's a rich literature on variants of this from Robbins, van der Laan, Siadas, Davidian, Tan, and many others that I'm not mentioning here, and most recently by Chernozhukov in the DDML framework. So it's a great tradition. The other aspect of ADML that I think is really elegant, it leverages the fact that the functional is a bounded linear operator to construct a generic debiased moment function, which Vasilis presented. And so you'll note the comparison between the W robust estimator, which tells you what the second nuisance parameter is in terms of the observed data distribution, is the propensity score, versus this construction of ADML, which just says, I just need a function of R and L. And of course, for this to be an observed data statistic, this has to be linear in R, because it has to be an indicator of R has to sit here, so you see Y. Okay? And what's beautiful about this is you don't need to know what the form of A star is. They give a generic approach to estimate it directly. And so the A star will solve this minimization problems that you can then perform, and you can use it without directly using the fact that A star takes this form in order for it to be the efficient influence function. And so this is great. This is a really flexible, very highly accessible tool that everyone can implement with their favorite machine learning methods, and allows one to use, as Vasilis demonstrated, really fancy ML tools to estimate A star using the above objective function. I think this is an exciting and promising development. All right, so let me turn to, I hope we have a few minutes for discussion. I have some questions for Vasilis. In this setting, you allow for user-specified Markov restrictions sometimes, at least in the paper. I know you didn't get a chance to get into it, such that N might not be unrestricted. How would you ensure that ADML leverages such restrictions to attain the efficiency bound? Okay, so that may not always be something that you want to pursue, but sometimes you may need to try to get as much efficiency as possible. And so one question is how to practically implement this. In dynamic settings, users' parameters estimation of ATML are nested. So you have these iterated estimation steps. This means that the error of estimation can propagate from early users' functions to later ones. This can induce more bias than necessary. How do you address this in practice? And so I know you have a way of addressing in theory in constructing these objective function, but in practice, the reality is if your outcome regression at the last time point is poor, the outcome regression at the first time point is going to be awful. And so have you thought about how to address this issue? A related problem is that in longitudinal settings, subjects often drop out so that data may be sparse at the end of follow-up. ATML estimates occasion-specific users' functions, which will likely fail in such settings. How can you address this issue? So to give you a sense, in biostatistics, when Jamie did this work with Miguel, for instance, with Marshall structure models, they allow parameters to be shared over time so that you borrow information from earlier time points. And so there's a little bias straight up there. And so my question then is, can you think similarly in this proposed setting of such strategies in a more formal fashion? Also, automation is great. It increases the use of the adoption of the methods. My question is, what is the cost of automation? One that I can immediately see is, and this is by no means just specific to ATML, how to tune users' functions estimates using either RKHS or deep neural net, if the aim is to minimize the bias or mean square of the AT and not necessarily the risk of users' function or that of the representative that you're using. So this is a hard question, and I'm curious if you have some thoughts. And then finally, I think you touched a little bit on this final point. What about problems where the representative is not a regression or density or function of such an object? And I'm thinking, of course, a problem that's close and dear to me, which is using proxies where the user's parameters tend to be solutions to integral equations. And I think you touched a little bit upon this by talking about IITs, but I was hoping you could say a little more. I don't know if you have enough time to cover all of this, but again, congratulations on a really beautiful piece of work, and I look forward to hearing your answers. Thank you.
Thank you very much, Eric. These are amazing questions, and thank you for the commentary. So let me try to address to the best that I can. Some of them are actually, like research questions that we can take offline. So the first one, as I said, there is loss that we're minimizing because it tries to minimize also the second moment of the Riesz representer. Many times it will find a Riesz loss that has a small variance, like a small variation. And so there is hope that maybe there's a theorem that Riesz loss will actually find something that is projected on the function space G. But sometimes I feel that in order to get the full efficiency, you need to restrict the functional space over which you're minimizing the Riesz representer. For instance, one very prototypical example is if you assume that your regression function is partially linear, then you need to minimize Riesz representers over partially linear functions. So that are linear in the treatment or something. So and so you can do that by explicitly restricting your Riesz representer to have this form, to be partially linear, and then most probably you'll get the efficiency. I don't know how to generalize that fully. In general, I think there are some, you can prove some theorems. If your G falls in some nice class of families, then it suffices to estimate the Riesz representer within the same space G. So that's actually something that you can show. So many times you can minimize the Riesz loss over the same function space as the regression function, and that will typically give you get you very close to efficiency. But a formal theorem I don't have at the top of my head, but these are things you can you can do to get lower variance Riesz representers. Yeah, the second thing is indeed true that like in our setting, the error that you are gonna get because we did not make any assumption about time invariance or you know like third parameters. The error rates that you're gonna get are gonna blow up with the time periods. So without further assumptions on some time invariance, I don't see how you can bypass that. I think it's even exponential blow up in the time periods. You will get rates that look like 2 to the m over epsilon square or something. So if m is really not a constant, the horizon of the time series, then you need to do, it's an open question how you do automatic debiased machine learning that's horizon free. And in practice, the one thing that I would do, like if I were to, one thing that's actually missing from the paper that's on top of our mind is actually having experiments to see how, you know, like these things behave with, say, neural nets or high-dimensional linear functions. One thing that you could do is the multitasking idea that we had for the neural net implementation for the static regime. You can also use it here if you want to learn representations that are shared across all the Riesz representers. Right? So maybe you have some large state space, but you know that the policy depends on some slow dimensional representation of that. Then you can use a multitasking approach where all of the Riesz representers you're minimizing are using the same sort of representation layer, and you're minimizing them simultaneously, right? So you can have losses. The output of one Riesz representer goes into as input to the other loss function, and so on and so forth. And you can simultaneously minimize all of those Riesz representers at once. And that most probably will lead to better finite sample performance. The third one is similar. I think I don't know how to easily do parameter sharing, other than when you do parameter sharing, essentially you're gonna be redefining what your estimate is. Right? And so whatever parameter sharing you do, that's gonna give you a new moment function that you need to use, right? That sort of like says that all of these different quantities are the same, and so I can average all of them. So you're going to have a different moment function, and then you can do automatic debiasing for that moment function. So I don't know if that should be incorporated into the automatic DML framework, or it's just a way of getting a better original moment to then debias because of parameter sharing. Maybe that's more towards the identification strategy, that once you have your assumptions together with your parametric restrictions or your parameter sharing restrictions, can we have more automated algorithms that use all of those assumptions, not just say the causal graph, but also these extra auxiliary assumptions to get a good original moment to then debias. That goes, I think, into more of like the line of research that I really like, which is incorporating external to the causal graph assumptions into automated identification algorithms. And the tuning, it's a good question. You know, like the current thing that I would recommend is just because it's just a square, sort of like a square loss, an uncompleted square loss. That's what I would do for hyperparameter tuning. Just do out of sample Riesz loss and choose the hyperparameters that minimize the out of sample Riesz loss. And that's what we do in practice in all of our experiments, like in the neural net and in the random forest experiments. And in the RKHS experiments, we exactly do that. We split samples and we choose the hyperparameters that lead to the smallest out of sample loss. That worked well for coverage and for mean squared error as a selection tool. Whether you want to use the target estimate for hyperparameter tuning, I think is an interesting question. I believe also Dominic has some paper on doing something different for hyperparameter tuning based on the target estimate, and you could use maybe ideas from that work within the AutoDML framework to inform the cross-validation based on what you're targeting after. But in some sense, the fact that you're locally robust tells you that it suffices to minimize mean squared error or Riesz loss error and then that would propagate to small theta error.
Vasilis, sorry, I think we have to
All right.
end the discussion now because we're already over time.
Sounds good. All right, so I'll stop there then. Thank you very much for all the
sorry
questions.
about that.
They're very insightful questions.
Yeah, so thank you again, Vasilis and Eric, for the great talk and discussion. So I'm just going to wrap up with an introduction to our speaker next week, who will be Lihua Lei from Stanford University, and he'll talk about double robust two-way fixed effects regression for panel data. So see you next week.